Hello and welcome back to another new lecture on the NPTEL course on advanced plasticity of solid continua. Now, if you recall, towards the end of the last lecture, we introduced to you the basic idea of why we need strain gradient plasticity, especially for mesh independent capture of the bands, plastic bands that can form. Okay, that's why we typically need strain gradient plasticity, if you recall. If you do not, then please go back to the last lecture and refresh your memory. Now, in this particular lecture, we will continue to use our variational setup based on the convex analysis that we have been using all through these various topics that we have covered. But today we will be talking of the primal formulation. I will explain what is primal formulation in strain gradient plasticity, and then we will go to the dual formulation as well, and we will see what kind of equations we get, especially the flow rules. Okay, so let us get going. So now if you just look at the basic problem of strain gradient plasticity, to start with, we use the same kind of elastic strain decomposition of the strain. For example, the total strain is decomposed into the elastic part, the plastic part, and a thermal part if there is thermal transport or heat transfer to be accounted for. If of course there is thermal strain epsilon theta h, then it basically we can think of it to be pertaining to linear isotropic thermoelasticity. So it will be related to a coefficient alpha t of linear expansion, thermal expansion, and theta 0 is a reference temperature, theta is the present temperature. So depending on the time difference, the temperature difference, we have the epsilon thermal. Okay, I is the identity tensor. So essentially this is the idea. So the state variables for us therefore will be the strain, which is the usual thing, the internal variables alpha. Okay, but what will be new here will also account for the gradient of the internal variables, grad alpha, and of course theta. Okay, recall that alpha consists of two quantities, one is the plastic strain and the other is the hardening related variables, kappa. Okay, so so this is basically the setup. The only difference here is that we have an extra grad alpha term, otherwise more or less it is the same as the kind of viscoplasticity formulations we have been discussing so far. All right, now let us go further and see what so the starting point of course is to have an idea of what the free energy density functional look like. Okay, so depending on your mechanics you have to construct it properly. So in this particular case, as in the other cases, we have always an elastic part, right? Recall that script C is basically the elasticity tensor, fourth order tensor, epsilon E is the elastic part of the strain. W kappa is the hardening related work, cold work, okay, that is stored and not dissipated. As you recall, the hardening processes essentially stores work. Okay, that is why you see essentially a non-zero positive slope in the stress strain curve. Then we have the thermal part, which is here, and as you can see that the thermal part essentially is a function of theta. No other parts are functions of theta, but the other parts which are of interest specifically in strain gradient plasticity are the parts which involve gradient terms in the internal variables. What are the internal variables alpha here? Recall it is epsilon p and kappa. Okay, and these are the gradient terms. This is one, this is the other. Okay, the first one is for epsilon p with a length scale L associated with it. Okay, any gradient term in mechanics, if it has to store energy and be a part of the free energy functional, will be associated with some kind of a gradient term, right? it is as if it is a Taylor-like expansion where it is any gradient term is associated with the length scale. So, it is as if it is a Taylor-like expansion where the length scale is the essentially some difference, some kind of a something like, if you just do f(x) equals, let us say, f(x0), this is some original term, the basic term. Then if you do a grad f at x0, okay, you take a dot product with x minus x0, you see this is the kind of a length, right. So, if you take the norm of that, that is essentially a length. So, you can think of this L to be a length through which the interactions happen between one point and the other. In that sense, this term as well as these terms are non-local terms. That is the reason why they are called non-local terms, because of the presence of these length scales. Okay. Right. So, to proceed further, we need to appropriately express the psi dot always, because the dissipation inequality involves psi dot. So, let us do that. Now, let us do term by term. So, the elastic part, for that if I take the time derivative, it is simply by Coleman-Knoll, it is del psi elastic del psi by del epsilon E inner product with epsilon E dot, but by Coleman-Knoll del psi by del epsilon E is just the stress. So, this is what we get. This is what we have been using for a long time, and we also know the stress strain relationship for a linear elasticity problem, which is related to the elastic part of the strain. The stress is related to the elastic part of the strain through the elasticity tensor script C. Then take also the derivative, time derivative of the expression for the strain as decomposed in terms of the different components, and we get this. Okay. So, if you actually use this in the expression for psi dot elastic part, then you get this simple expression, which is obviously there for you to, it is pretty clear to you, no explanations are needed in this particular case. So, for the gradient term involving epsilon p first, let us take the time derivative also, because that also appears as part of the free energies. So, ddt of the gradient term involving epsilon p, that is the plastic strain, is simply this. So, this is the length scale square, gradient of epsilon p inner product with gradient of epsilon p dot. Now, recall that gradient of epsilon p dot is the same tensor of the same order as gradient of epsilon p. If epsilon p is a second order tensor, then gradient of epsilon p will be a third order tensor, right. And so is gradient of epsilon p dot. Okay. But once you take the inner product, it becomes a scalar. Okay, right. Now, we can proceed further with our discussion. So, we can actually do an exactly similar job with the extra term, the other term involving the gradient of the hardening variable kappa. Okay. First, so let us not do that. It is just the same, except that instead of L square, you will be having LK square and all that. All right. So, let us take the other term WK, which is the cold work stored due to hardening. Okay. The stored work due to hardening. So, this is W dot is by chain rule del W by del kappa, kappa dot with appropriate inner product thrown in between. Now, we also can take the thermal part and its time derivative. It simply gives you by chain rule psi theta dot is minus del psi by del theta, because psi theta is the only part which depends on theta. Okay. So, I can as well say minus del psi by del theta is essentially equal to del psi theta by del theta, you understand. So, you also know by now that the entropy, local entropy density is given by minus del psi by del theta. So, we can write psi thermal dot to be equal to minus eta theta dot, okay, by the standard chain rule. Now, if we take all the terms together, all right, for psi dot, we have these terms, right, term by term, just write all of them. Okay, see, we have all the terms put in appropriate order, right. Now let us use the Clausius-Duhem inequality, the dissipation inequality, as you know. So by now it may have been, you may have got yourself familiarized with the expression. So it is simply the external work, this is the stress power given here, minus psi dot minus the heat transfer related, the dissipation, which is 1 by theta, the heat flux Q dot grad of theta. That has to be greater than or equal to 0, right? You recall that surely. Now we have to put in this expression for psi dot the psi dot that we have just got here, all right. So let us do that. Then you see, as always, the stress power cancels out, leaving us with the terms which multiply through the inner product with sigma, the stress. These terms only multiply with stress through the internal variable terms, right? The epsilon p dot, epsilon, okay, the epsilon theta dot is an extra term here, right? Then there is kappa dot, right? Yeah, kappa dot term is here, okay, and so on, and of course the gradient terms, okay. Now you see that we really do not, so the strain gradient terms are basically the terms where the gradient term appears in both the factors. So we can actually do better than that. Basically, if we want only epsilon p dot, what is epsilon p dot? It is an incremental change in epsilon p, right, in unit time. So if we want to free it up so that later on if we replace instead of epsilon p dot, replace it by an incremental variational change in epsilon p, right, then by treating epsilon p dot like that, we see that this term is not suitable for that. Similarly, this term is not the right term. We have to remove the gradient from here so that we can actually free epsilon p dot and kappa dot, okay. So therefore we need integration by parts, and if we do that, locally we can state this way. This is the left side, in this expression, the term which is a pure divergence will lead to, upon integration, a boundary term, and the other term is what is actually important, which will be living even inside the body, okay. So if we ignore the boundary terms and write locally, because the boundary comes not as part of the local transfer of force, so then we can actually take only this term, okay, for the equality, right, ignoring the boundary effect for the time being. And similarly we can treat the other gradient terms, okay, other gradient term involving grad kappa dot. Then collect all the terms properly. That means select terms in such a way that these factors come out, okay. So this and theta dot, okay, so these factors come out, right. Now the thing is that you see that what we get essentially is not, so far we have been getting terms like for epsilon p dot, the factor that we have so far been getting in all our experience with other models is just sigma. Now we have an extra term which is here, divergence of L square grad epsilon p, which is an extra term in epsilon p, the plastic flow. Similarly for the hardening term also a similar expression involving the gradient of kappa is there, right. So the driving forces corresponding to these two terms, these two rates, right, they seem to be having a different structure now, okay. They have a structure in which a second order derivative is coming in, because why second order? Because grad epsilon p, think of this, grad epsilon p, it already has a first order derivative, and this divergence outside adds another order, right. So this is a second order derivative in epsilon p that comes in. Similarly you can argue for the hardening term. All right, now let us now talk of the primal, continue to talk of the primal approach. So For the term involving the this sigma epsilon dot theta, that is the thermal expansion term, we can actually put the expression for epsilon dot theta, which we used some time back, which we postulated some time back in terms of alpha theta. So, you see there was an identity tensor there. Okay. So, that inner product with sigma gives you trace of sigma, and essentially you get this. Okay. So, combine the thermal terms now together, because now we have a theta dot from here. Earlier there was a theta dot only here, right. Now we have an extra theta dot coming from here too. Okay. So, combine this. So, we can take theta dot outside, and this is the factor. So, we essentially by Coleman-Knoll, theta is actually a state, it is not history dependent. So, its coefficient must therefore vanish, right, by the same arguments as put forward by Coleman-Knoll. I mean, basically we have been discussing this for quite some time, and please recall. So, therefore, what we get from here is that eta is minus alpha t, which is basically the coefficient of linear thermal expansion times trace of sigma, but we already know that eta is minus del psi by del theta. So, we have this identity as well. Okay. So, if we impose the, so in order to be consistent with the second law of thermodynamics, then this has to be respected as well. Okay. So, right. Now, let us actually take a simpler route. That means, we will see, our objective is to make the dissipation strictly positive, right. So, let us make these term by term, not term by term fully, but this term I will treat separately. Let us decide to do that, right. That means, I want to ensure that this term is separately greater than equal to 0, which will also satisfy the second law. Okay. So, but in this doing so, you use the Fourier's law, minus k grad theta is nothing but the heat flux, which ensures that this term is definitely greater than 0. So, we can actually throw this out. We have done that earlier also, and bother only about the mechanical part of the incremental work done per unit time by by the let us talk about the reduced dissipation inequality, that is to say. Okay. So, this is the term that we have to make greater than equal to 0. Okay. And we already know that there are two such forces that we already got, one as a factor of epsilon p dot from here, remember, these were the forces that we got. One is this is essentially x epsilon p dot, correct. Similarly, this was the force, this was x kappa dot, right, or probably we are calling it x kappa, I do not remember, anyway it does not matter. Okay. So, what is, yeah, x kappa, okay, we are not putting dot here, we are just saying x epsilon p, right. So, basically we have already got these expressions for x epsilon p and x kappa, right. So, these work on epsilon p dot and kappa dot respectively to produce power, and remember now that so we will be using this now, okay, into this expression. Let us see. Right, but before we are able to do that, now let us take the variational route. Okay. So far we are only discussing about psi dot, right. But in the variational route, we have another term which actually is contributed to by the dissipation potential, which we have introduced. And the dissipation potential can have its own structure, it has to be convex, right. We take it in a very simple form now for the time being. This is not Perzina type viscoplasticity, remember, because if I take it in this form, then there is no strictly plastic flow without viscosity. There is no notion of yield surface, because viscosity comes right from the beginning as alpha starts evolving, and therefore there is no yield surface. Basically, plastic flow starts right as you apply the input some external agency, that means in the form of some external forces and so on. Okay, this is that sort of a model. Okay, we have discussed this model also some time back when we discussed viscoplasticity. in the beginning. Okay, so here this script D has this structure, right. It has a coupling term also involving the coupling between the epsilon p and alpha and the diagonal terms, right. Typically we actually neglect the coupling terms. I mean, if there is any reason for you to understand based on the physics that these coupling terms are important, then put them in. For the time being, let us neglect. A common choice, so therefore for the different blocks will be just dpp is just eta p. Eta p is basically a constant. Script I symmetric means it is basically a fourth order tensor which acts on a symmetric second order tensor and produce the same symmetric second order tensor. So it is an identity transformation on all symmetric second order tensors. Okay. So eta p is a scalar. Okay. P means it is correspondent to epsilon p. It is basically the relaxation or the the damping associated with the plastic flow. Similarly, the damping associated with the viscous damping associated with the hardening is eta k. Okay. All right, we assume that eta k is okay. Eta k is also a scalar, and for the time being we assume that kappa is also a scalar. Okay, eta kappa. Okay, all right. Now, so the coupling, let us take 0 as I have already said. I have already defined script I sim. So if it is acting on a non-symmetric second order tensor, then it will produce the corresponding symmetric second order tensor. All right. So it is useful for defining strain as a symmetric tensor, right. So therefore this leaves us with the following expression for the dissipation potential. What is the expression now? The expression for the dissipation potential is given here. Okay, so this is the expression for the dissipation potential. So you can see that this expression is very similar to the squared type of energy expanded by both the terms with eta p and eta k acting as the corresponding viscous damping terms. All right. Now, so basically therefore with this phi we have the variational formulation ready. I mean, variational formulation is not ready, but the stage for the variational formulation is now set. So all that we have to do, we have got the expression for psi dot and we have got the expression for phi, correct, and that would be my some kind of a potential. I do not know, I mean maybe you can call it by R or something, right. Now if you recall that this is the potential we have always been minimizing, always been taking variations of and setting to 0. We are driving this potential to stationarity throughout the entirety of our work. In this particular case, what was the difference? The difference was that there is no change in phi per se because of the strain gradient plasticity, nothing. The expression for phi did not have any strain gradient effect, right. It still had the dissipation because of the fact that there is this dependence only on epsilon p dot and kappa dot. They produced the dissipation. What did grad of epsilon p dot do? It did not produce dissipation, it produces a stored energy like thing, right. So basically from the structure itself all that has gone, all the gradient effects have gone into psi dot. So from the structure itself you can understand that what we are trying is essentially an energetic form of the gradient information driving the mechanics, okay, the energetic form. If you have very clear understanding that there should also be a dissipative structure to it, then you should be able to change, if you have a very strong reason to suspect it, which you have to be very sure of, then you can include those effects even here, okay, in phi. But typically the effect of the gradient plasticity and the formation of bands happens because of the change in the microstructure. The change in the microstructure cannot dissipate energy because then that change will be lost, right, if the energy is dissipated. the energy which produced that change in the microstructure per se, if it is lost, then the microstructure cannot remain in that state, right. So that is the reason why psi essentially is the quantity which contains the gradient effect. So now we are ready, I mean, having said all that, you also recall another stuff, that R, the variational functional, has two roles to play. One is the local minimization, which produces the flow rule, right, the flow rule for you, and the global minimization, which produces the balance laws. Global minimization, by that I mean integral over the entire body. Okay, so these are the things that we need to do now. Okay, so so this is exactly which we'll be doing now, starting from the next lecture. Till then, I hope you have followed up to this. Basically, we will be coming back into the next lecture, talking about the same R and trying to extract the flow rule, which will be quite different for strain gradient plasticity, an interesting form that I will share with you. And also I will be talking about the in the next lecture the how to actually do the global variational formulation, and then so I will put the global variational formulation first as a theoretical exercise, and then we will also do it in one of the future lectures in an incremental way, so that you can actually extract the stiffness, tangent stiffness from there and implement it in a finite element framework in the same way that we have been doing for the other models. So thank you for your attention to this much, this part of this lecture, and we will see you back soon. Thank you.